Welcome friends. We are discussing network solving techniques. In the last part, we are discussing module 4. In the last part, we have discussed few techniques where we have seen first uh, potential divider circuit, then we have seen current division rule. Thereafter, we have solved one problem regarding a very useful technique, which is star delta and delta star transformation. So now moving on with our next topic, we have very important two techniques. First one is called node analysis, which is philosophically revolves around KCL, which is called Kirchhoff's current law, and later on it's called mesh analysis, which is philosophically revolves around Kirchhoff's voltage law, or in short KVL. So let us discuss these two techniques in details. So first, Kirchhoff's current law. Let us say we have a junction like this where different currents are entering or maybe leaving. So according to the KCL, it states that net current flowing into any node is equal to the net current flowing from that node. That means it's net current incoming, net current incoming, according to KCL, net current incoming is equal to net current outgoing. So if you consider this simple circuit, figure 5, we can see that I1 is flowing into the node, I5 flowing into the node, and I4 flowing into the node. So they are called incoming currents to the node. Let us say this node is X. So this I1, I4 and I5 are the current entering into the node, and this I2 and this I3 are, these two currents are leaving from the node. So these three currents, I1, I4 and I5, they are incoming currents, and I2 and I3 are leaving currents. So net current incoming, that will be equal to net current leaving. So this is the statement of KCL. We shall solve different problems using this KCL nodal analysis later on. Let us first revisit, or let us first discuss what is KVL. Now KVL states that total potential drop across a mesh or loop, whatever it may be, mesh or loop, is 0. That means if you consider a mesh or loop, total potential drop across the mesh or loop is 0. So if you consider the figure 6, let us understand the statement of this law. Now, to understand the statement of the law, let us first try to understand what is the polarity of the potential. So let us say if we have a resistance, and suppose a current is flowing in this direction, then polarity of the potential should be marked in this way. The left hand side is positively polared, and the right hand side of the resistance is the negatively polared. Why? The reason is quite simple, because current is flowing. Current should flow from higher potential to lower potential. As simple, water flows from higher altitude to lower altitude. So current, just like that, current will flow from higher altitude or higher potential to lower potential. So if suppose this is a current, this is the resistance R, and if a current is flowing I in this direction from left to right, then this drop, potential drop, that is IR, potential drop, which is equal to IR, the polarity of this potential is given by this plus and minus. Left side of the resistance is plus, right side of the resistance is minus, because current should flow from higher potential to lower potential. It cannot be the reverse. So now, if two such potentials is arranged in this way, let us say this is one potential V1 and another potential is, let us say this is V2. So this is called additive polarity. This is called additive polarity. They are very important to understand and to write the actual KVL equation. Additive polarity. On the other hand, if any two potential is arranged in this fashion, if this is plus minus, let us say this is V1, and this is minus plus, let us say this is V2, then this is called subtractive polarity. Subtractive polarity. So let us quickly understand, if two polarities, two potentials, if arranged in this fashion, plus minus, again plus minus, then this is called additive polarity. So net voltage appearing across this, it's called V1 plus V2. V1 plus V2. However, if the potentials or polarities are arranged in this fashion, this is plus minus and V2 is just reverse, minus plus, then it is called subtractive polarity, and the net potential across these two resistance or two elements is V1 minus V2, or maybe V2 minus V1, depending on which is greater and which is smaller. So just please try to understand, plus minus, it stays polarity of the potential or voltage drop. If two polarities or if two potentials are arranged in this fashion, plus minus, then that is called additive polarity. The net voltage is summation of those two, V1 plus V2. And if this polarity is arranged in this fashion, plus minus, plus, that means two same signs are occurring simultaneously, then they are called subtractive polarity. It is either V1 minus V2 or V2 minus V1, depending on the magnitude. So if you understand this elementary concepts, now let us consider figure 6. We have a voltage source V, we have a resistance R1. If we have a resistance R2, then we have a battery E. Now initially we have assumed the polarity of the potential or voltage source as this plus minus, upper plate is plus, lower plate is minus, and potential, the battery of the potential is upper plate is plus, lower plate is minus. Now we have assumed current direction in this. So the current flowing through R1 through this, in this direction, so it should be, the left hand side of the R should be plus and right hand side of the R1 should be minus. Again, the same current will flow through R2, so the same current directions, it indicates the left hand side of the R2 will be plus, right hand side of the R2 will be minus. So this drop actually I into R1 drop, I into R1 drop and I into R2 drop. This will cause two potential drops. Now we have four drops, four voltages. Okay. We have V, then we have IR1, then we have IR2, then last we have E. These four drops we have there. So now if you consider this, you see, let us start with this V. The polarity of the potential is minus plus. So if you compare V and IR1, they are subtractive polarity because it is arranged in this fashion, minus plus, then plus minus. So they are subtractive polarity. They are not additive. Now if you again consider these two, then that means IR1 and IR2, they are called additive polarity because plus minus, they are arranged in additive fashion. So these two are additive polarity. With these two potential drops, we have battery. The battery potential is plus minus. So again, if you consider plus minus, again, if you consider battery, it is again plus minus. So these three potentials, IR1, IR2 and E, these three are additive polarity. These three are additive polarity, and with these three, V is subtractive polarity. So that is why we have written this equation as V plus IR1 because it is a subtractive polarity. That is why this minus came. The same reason IR2 with a minus sign because it is a subtractive polarity. And with this battery voltage minus E. So in other words, we can write left hand side V, that should be is equal to right hand side all the other, all additive polarities. That means IR1 plus IR2 plus E. It is both are the same. It is the different approach through which you can understand this concept. You can write additive polarities in one side of the equation and you write subtractive polarities at other side of the equation, and those additive polarities and subtractive polarities should be equal and opposite. If you do that, then net potential drop across the loop will be 0. Net or total potential drop across the mesh or loop will be 0. So if we write the KVL equation, it should be V is equal to IR1 plus IR2 plus E because these three are additive, and with this V will be subtractive to all these three. So that is why it is written V is equal to IR1 plus IR2 plus E. Now let us argue on one point that we have assumed. Let me erase all these things. We have assumed that current is flowing in this direction. We have assumed it. But what is the guarantee that the actual direction of the current is from battery to or the voltage source to battery? The current direction could be in this way also, from right to left. So what is the guarantee? And which is the correct? As current cannot flow in both the directions. Either it will flow from left side as it is assumed in this problem, or it will flow from right to left. It cannot be both. So which one is correct? So why we have assumed, why you have assumed this assumption? The answer is, whatever be the direction of the current, it is, before solving the problem, it is not possible to know. Before solving a problem, suppose if you have this circuit, figure 6, it is not possible to know what is the actual direction of the current, whether it is from V to E or it is from E to V, it is not possible. However, to start the problem, you must choose one direction. You must choose one direction. So at first, you choose one direction as per your wisdom. Whatever you think, as per your wisdom, you assume one current direction. Now, do not change. Once you have assumed, do not change. Whether you have assumed clockwise direction or you have assumed anti-clockwise direction, absolutely no harm. You can assume whatever you like. But once you have assumed, do not alter or do not change it further for the rest of the problem. That is very important. There is no strict rule that you must choose clockwise or anti-clockwise. No, there is no. It is absolutely your wisdom, your choice what to select. However, it is always recommended. To choose conventional current direction. It is always recommended to choose conventional current direction. What is conventional current direction? Because it is actually, you see, current is injected by the voltage source. Current is injected by the voltage source. You see, that is why voltage source, if this is the voltage source V with magnitude V, so it will inject some current I. That is why we have assumed in this direction, okay, from left to right, or maybe in the clockwise direction we have assumed. However, if you still assume reverse direction, it is no harm. It will cause no harm if the assumption is reverse. So absolutely, it is your wish what direction you choose. But if you choose one direction, whether it is a clockwise, anti-clockwise, no problem. But once you have chosen, do not alter or do not change it further. Now, according to the direction of the current, assume direction of the current as per your assumption, mark polarity of the every potential. That I have marked here. I have chosen this current direction. For the time being, I am erasing this arrow. As per your direction, as per your assumption, mark the polarity. So you see, since I will be flowing through R1, so a potential drop will come in this resistance. That is why this potential will be polared as this plus minus. Left hand side is R, left hand side is plus, right hand side is minus, because current will flow from higher potential to lower potential. In this direction, current will flow. Similarly, IR2 drop will cause this polarity, because current will flow from higher potential to lower potential. So mark polarity. That is very important. Mark polarity of every potential. It may be source or it may be potential drop across an element before writing KVL equation. So it must be written. If you follow these protocols, there is a very less probability of not making mistake. Okay. So how come this polarity? Because it is totally dependent on the direction of the current as per your assumption. Okay, now frame KVL equations as per additive polarities and subtractive polarities as shown in figure 6. So these are the standard protocols which you should follow to minimize your error. First you choose one current direction as per your wisdom. It is absolutely cause no harm if you choose anyone. That means you can choose clockwise or you can choose anti-clockwise. No issue with that. But If you choose clockwise, for this problem it is clockwise direction, so I cannot change it further for the rest of the problem. While solving the problem I cannot change. Then according to the assumed current direction, please mark polarity, potential polarity of the potential as shown. And once the polarity of the potential is marked, you write the KVL equation by identifying which are the additive polarities and which are the subtractive polarities. In this way, KVL equations are written. So this is the very small illustration. Now let us solve one problem with, first we solve one problem with nodal analysis, then we will solve one problem with mesh analysis. So let us say, consider this figure 8. Consider this figure 8 where you need to find the current flowing through 10 ohm resistor. So this is the 10 ohm resistor. You need to find the current flowing through this 10 ohm resistor. Now it is to be noted that this currents marked by red, actually it is not given in the problem, it is drawn additionally. This with this red, this I1, this I3, this I5, this I4, this I2, all these currents marked with red, drawn in red, all these polarities plus minus, they are not actually in the problem diagram. It is drawn additionally to make the picture more clear to you. So actually this diagram should be look like this. We have a source. Let me draw the diagram first, then you can compare. So this is a circuit. It is a simple circuit. We need to evaluate the current. This is 16 volt source. This is 4 ohm. This is 10 ohm. This is 4 ohm. This is again 4 ohm, and this is 16 ampere. This is the current, or this is the circuit. And additionally, whatever you are seeing with this, all these by this red ink, all they are drawn additionally to make this diagram more clear to you. Now we have assumed two nodes across this 10 ohm. This node is X and this node is Y. So what is the standard protocol? We have to first assume the current direction as per our wisdom. So that we have assumed first. Let us say that 16 volt source will inject one current. That current is I1. And since this is the ground node, so one current should be flowing from X to ground in this direction, which is actually I3. And from X to Y, let us say one current will be flowing in this direction, let us say I5. Again, this 16 ampere current, it is I2, we have assumed I2, and from Y to ground we have another current that is called I4. So we have assumed this conventional current direction at very first. So what is KCL at node X? If you look, carefully, you see at node X we have one current entering I1 and two currents leaving I5 and I3. So entering current is I1 and leaving current is I4, I3 and I5. So according to the KCL, net current incoming, it must be equal to net current outgoing. So I1 is equal to I3 plus I5. So that is mentioned in equation 1. I1 is equal to I3 plus I5. So now what is I1? You see, this I1 is caused by this potential drop appearing across this 4 ohm resistance. So this node has got voltage Vx and this is 16 volt. So this I1 is nothing but 16 minus Vx divided by 4. This current, actually this current is flowing, this I1 current is flowing due to the potential difference between this 16 volt source and Vx. So the potential difference is 16 minus Vx, and according to the Ohm's law, V by R, that is 16 minus Vx by 4 ohm, which is the I1. Now what is I3? So I3 is nothing but, you see this current is I3. Now the potential of this node is 0. This is 0 volt. So this is Vx, this node is Vx. So current flowing through this 4 ohm resistance, which is I3, it is nothing but Vx minus 0 divided by 4, which is Vx by 4. And what is I5? I5 is nothing but, you see, I5 is, since we have assumed current flowing from X to Y, that is why Vx must be greater than Vy. Vx must be greater than Vy according to our assumption. According to our assumption. It could be reverse also, but according to our assumption, since we have assumed I is flowing from X to Y, that means Vx must be greater than Vy. So that is why we can write I5. We can write I5, that will be equal to potential difference Vx minus Vy, that divided by 10. So we have got these three relations. So now we can write the KCL equation. So first we have I1 is equal to this, which is 4 minus Vx by 4. I3 is equal to Vx by 4 and I5 is equal to Vx minus Vy by 10. So if you solve them from equation 1, then we should get a equation is this 3 by 5 Vx minus 1 by 10 Vy, that will be equal to 4. Because it is very simple. You see 16 minus 4 by Vx, that will be 4 minus Vx by 4, that will be equal to Vx by 4 plus Vx by 10 minus Vy by 10. So if you bring this Vx by 4 this side, so if you put LCM, it will be 20 . So it will be 12 Vx minus Vy by 10, that will be equal to 4. So that is why it is written 3 by 5 Vx minus 1 by 10 Vy, that will be equal to 4. That is equation 2 for you. Now coming to the node Y. Now coming to the node Y side. So again, if you consider node Y, so with respect to node Y, so if we draw the diagram again, this is voltage source 16 volt, we have a resistance, again we have a resistance, okay. So this current we assumed I5, this current we assumed I4, this current, this source is 16 ampere, which we assume equal to I2, right? So we assume this node was Vx and this node was Vy. So now with respect to node Y, let us say I5 and I2, these two currents are now entering, and I4 is leaving. I4 is leaving. So we can write I5 plus I2, that is in entering current, is equal to I4. Okay. So I2 is 16 ampere. It is well understood. I2 is equal to 16 ampere here. I5 is already calculated, or it is known, that is Vx minus Vy by 10. Now what is I4? Now as it is mentioned, this node is at zero potential. So I4 is nothing but this potential is Vy. So Vy by 4 ohm, because this resistance is 4 ohm. So I4 is Vy by 4. So if you, from equation 3, if you use this, so you will get a equation number 4, which is equal to this, minus 1 by 10 Vx plus 7 by 20 Vy is equal to 16. So we have equation 2, we have equation 4, these two equations. So if you now solve, first you will get Vx is equal to 15. First you will get Vx is equal to 15 volt. Vy is equal to 50 volt. Vy is equal to 50 volt, which is very interesting result, which we will find very interesting result. Now before explaining, I want to clarify something. Let us say we have a resistance. Let us say we have a resistance and we have assumed one current direction as per our wisdom. As per our choice, we have assumed. However, in actually this is our I. Actually, this is I. This is our assumption. We do not know what is the actual current direction. But let us consider actually current is flowing in something in this direction. It is the direction of the current. It is the actual direction of the current in this direction. From right to left, it is the actual direction, I actual. So the immediate question comes, will be the problem will be, or the solution will be wrong? No. The answer is no. If your assumption does not match with the actual current direction, then you will get something like this. Answer should be something like this. I should be is equal to minus 2 ampere. So in actuality, current was flowing 2 ampere, but since your assumption is just negative or just reverse, then you will get answer with a negative sign. That is the only thing you will get, with a negative sign. So if please remember, if your assumption does not match with the actual current direction, your answer will be same, but you will have a negative sign with your answer. Now coming to this problem, we have assumed current flowing in this direction I5, that means current flowing from X to Y. However, we have solved and we get Vy greater than Vx. Vy greater than Vx, right? So that means actual current direction from Y to X. This is actual current direction, not what we have assumed. So actual current direction is I actual, or current flowing through 10 ohm resistor is nothing but 50 minus 15 by 10, which is equal to 3.5 ampere. Now what is the direction? From Y to X. This is the actual direction, but before starting the problem, we have assumed the current flowing was from X to Y. However, the actual direction is from Y to X. So our assumption was not matching with the actual direction, but still it will not causing any harm, just we will get a negative answer. So from the solution itself it shows Vy is greater than Vx, therefore it is a quite strong result, which indeed is showing that current must flow from node Y to node X, because Vy is greater. Current is flowing from higher potential to lower potential. So the magnitude of the current is 3.5 ampere. So the direction you must mention, it is from Y to X. So that is all about KCL. We first consider node X, or one node at a time, and you try to figure out how many currents are associated with that particular node. For an example, with X, let us say if you consider X node, so there are three currents, I1, then I3, then I5. These three currents are associated with node X. Try to write KCL equation from the understanding of the incoming current and outgoing current. Then using Ohm's law, try to write down what is the current equation. For an example, here I1 is equal to this 16 voltage minus Vx divided by 4. 16 minus Vx divided by 4, that becomes I1. In this way, you write all the current equation and you get, for two nodes you will get two equation, and when you solve, you will get the answer. From the answer you can see a very interesting thing. What you have assumed is actually reverse, is actually not matching with the actual case. Actually Vy is greater than Vx. That means your assumption was just reverse, or you can say negative. That means your answer, the current which you assume should flow from X to Y, now it is actuality. In actuality it is flowing from Y to X, because Vy we have obtained greater than Vx. So with this we can proceed to our next problem, that is on KVL. So this is a problem of KVL. You consider figure 9. You need to evaluate I1, I2, I3. You need to evaluate I1, I2, I3. Okay, so this is mesh number 1. This is mesh number 2. This is mesh number 3. There are 3 meshes. So we will write 3 mesh equations. We will write 3 mesh equations. So let us write one by one. If you consider mesh 1, let us figure out, or let us make a list how many potentials are there, how many potential drops are there. Okay, so first we will have potential as this source, 2 volt source, right? This is one drop. So this is 2 volt source is one potential. Second potential drop is this potential drop across this 2 ohm resistor. Now what will be the current flowing through this 2 ohm resistor? Now again another important observation, we have assumed the polarity of the potential is this. Polarity of the potential should be like this. This is our assumption, right? Left hand side is plus, right hand side is minus. So if you look closely, then 2 currents are flowing through this 2 ohm resistor. Please try to understand this fact. There are 2 currents flowing through these 2 ohm resistors. One current is I1. This current I1 is flowing. Right, so I1 is flowing through 2 ohm resistors, and another current is flowing I3. This is also flowing. They are called mesh currents. So I1 is called mesh current. That means this current will be flowing continuously through this mesh. Similarly, I2 is the mesh current of mesh 2. It is continuously flowing through the mesh 2, and I3 is the mesh current of mesh 3. It is continuously flowing through mesh 3. So I1 is also flowing. So as a matter of fact, as it stands from this diagram, I1 is flowing through 2 ohm resistor. I3 is also flowing through this 2 ohm resistor. So if I draw it separately, let us say this is 2 ohm resistor. So I1 is flowing in this direction, and I3 is flowing in this direction according to the current direction given in the diagram. Okay, so I3 you see clockwise current. So this is the current through our 2 ohm resistor, right? And for I1 it is again clockwise current, so it is flowing through this. However, if you have considered the potential or polarity of the potential like this, left hand side plus, right hand side minus, so the net current must be flowing from right. So due to this fact, the current flowing through 2 ohm resistance must be I1 minus I2 as per our convention. This is very important, as per our convention. Because we have assumed the left hand side is positively polared, right hand side is negatively polared. So net current should be flowing from higher potential to lower potential. So this should be the actual current direction through 2 ohm resistance. So you see I1 is flowing from left to right, I3 is flowing from right to left. So the net current flowing is I1 minus I2 through this 2 ohm resistor. So the potential drop across 2 ohm resistor is 2 into I1 minus I2. Now, for the time being, let us not consider this current source. I'll tell you why later on. Next, you consider please this 1 ohm resistor. Let us consider this 1 ohm resistor. Again, from this 1 ohm, again with this 1 ohm, if I try to draw, this is 1 ohm resistor. Again there are 2 currents, I2 is flowing. clockwise current, again I3 is flowing in this current, this direction, again in the clockwise direction, and polarity is assumed in this fashion, left plus, right minus. So this is plus, this is minus. So the net current flowing through this 1 ohm resistance is I2 minus I3. I2 minus I3. So the potential drop across 1 ohm resistance is 1 into I2 minus I3. Last we have this 2 ohm resistor. Last we have this is 2 ohm resistor. There only one current is flowing because 2 ohm resistors is the only resistance that belongs to mesh 2 alone. Otherwise this 1 ohm resistor is common to both mesh 3 and mesh 2. This 1 ohm resistor is common to both mesh 3 and mesh 1. This 2 ohm resistors is common to both mesh 1 and mesh 3. That is why two currents must be considered. However, for this 2 ohm resistance, only one current should be flowing, that is 2 ohm. So the potential drop across this 2 ohm is 2 into I2, and this is considered as plus minus. So now if you consider these three potentials, 2 I1 minus I3, this should be 3. Second one will be 1 I2 minus I3, and third one will be 2 I2. These three are additive polarity because plus minus plus minus plus minus. So these three will be additive polarity. So they are all added. Let us say that 2 into I1 minus I3 plus 1 into I2 minus I3, and therefore 2 I2. And this 2 volt source is subtractive polarity. You see, minus plus plus minus. So 2 volt is subtractive. So we can make summation of all these three equal to 2. So now if you solve this, you will get a solution or equation coming up 2I1 plus 3I2 minus 3I2 is equal to 2, which is given by equation 5. So we have got one equation. Now why I do not consider this current? What about this current source? Now we have already made a mention that in the module 1 that if a current source, this is a current source, 1 ampere current source, right? This is a 1 ampere current source. If a current source is common to both any mesh, then those two meshes are considered to be the super mesh. Because you cannot apply KVL. Why? Because you do not know, you know the current 1 ampere, but you do not know the resistance of this current source. You do not know the resistance of the current source. That is why you cannot write, or you do not know the potential drop across this branch or across this node, these two nodes. Let us say this node is X and this node is Y. You do not know the Vxy because you do not know the resistance of this ammeter. You know the current, it is 1 ampere, but you do not know the resistance. That is why potential drop across this branch XY it's not possible. That is why those two meshes, which is both common to 1 ampere is current source, they are clubbed together and considered as a super mesh. Okay, so it is considered as a super mesh 1, 2. This is called super mesh. Now moving on to the next, you see if you consider the mesh 3, so basically this is not a mesh 1, it is called super mesh 1, 2. It is called super mesh 1, 2. Now if you consider the mesh 3, so again there are three potential drop. One is this 2 ohm. There is a potential drop across 2 ohm resistors, which is 2 into I1 minus I3. Polarity as mentioned. Second one is this 1 into I2 minus I3. polarity as mentioned, and last one will be this, third one will be this. Okay, this potential drop across 1 ohm resistor. Now this 1 ohm resistor in the mesh 3, the polarity is assumed in this way, plus minus, left side plus, right side minus. So I3 is flowing from left to right in the clockwise fashion. So the potential drop across the 1 ohm resistance is only 1 into I3. So if you consider now polarities plus minus, they are additive. Now if you go again to this 1 into I3, it is coming plus minus, minus plus. So these two are subtractive. So these two are additive, they are subtractive. So the correct equation will be 2 into I1 minus I3 and 1 into I2 minus I3, they are additive. With that 1 into I3, it is subtractive. So then at the other side of the equation, so if you consider or if you solve, we will get an equation like this, equation 6. And finally you have another equation, this 1 ampere source, you see through this current, you see this current is let us consider this current is I2 and this current is I1. So this 1 ampere flowing from bottom to top in this direction. So this 1 ampere must be equal to I2 minus I1. 1 ampere must be equal to I2 minus I1. That is our third equation. So equation number 8. Now if you arrange these three equations, equation 5, 6, 7 in a matrix form, we will get this matrix. You will get this matrix, right? So what will be the solution of this matrix? So I1 will be, the solution of this matrix will be, the current I1 should be delta 1 minus delta, I2 should be delta 2 minus delta 2 by delta, and finally I3 would be delta 3 minus delta. Now what is delta? Delta is the determinant of the main matrix, that is 2, 3, minus 3, 2, 1, minus 4 and minus 1, minus 1, 0. This is the determinant of this matrix. So if you solve, it will coming out to be 2 into 0 minus minus 4 into 1. This is the first term. Then second term will be plus 3. So here it ends. So it starts with this minus 4 into 1, minus 4 into 1 and minus 0 into 0. So it will be 0. And lastly we have minus 3 into 0 into 1 minus 1 into 1, that is 1. So if you solve this, you will get this one as 11. So this is the determinant of this matrix. Now what is delta 1? Delta 1 is the determinant of the matrix. Now what is delta 1? Delta 1, when this right hand side column matrix, is substituted at the first column, and that matrix become this. You see this 201 is replaced here. 201 is replaced here at the first column. So the delta 1, the determinant of this matrix, and it will be, if you solve, it will be coming out to be, let us solve, this determinant will be 2 into, so if you consider these two, then these two respective, this row and this column must be omitted. Then we should conduct a cross multiplication, 1 0 and this way. So 1 into 0 minus 4 into 1. Then plus 3. Then we will have minus 4 into 1 minus 0. Then lastly we have minus 3. We have 0 into 1 minus 1. So if you solve this, you will get minus 1. Now similarly, if you solve delta 2, what is delta 2? Now delta 2 means this, you see this column is replaced at second column. So now use this second matrix, this is replaced by this column matrix 2 0 1. So if you similarly delta 3 is 2 0 1 is replaced at the third column. So if you evaluate delta 2, you will get 2 into 0 into 0 minus 4 into 1 plus 2 into minus 4 into minus 1 minus 0, then minus 3 into 2 minus 0. So if you solve, you will get this one as 10. And lastly, if you solve delta 3, the determinant of this matrix, 2 into 1 into 1 minus 0 plus 3, 0 into minus 1 minus 2 plus 2, that is 2 into 1 minus 1 into 1. So if you solve this, you will get 2. So now if you solve this, delta 1 will be coming out to be, minus 1. Delta 2 will be coming out to be 10 and delta 3 will be coming out to be 2. So if you solve I1, that will be equal to delta 1 minus delta, it is coming as minus 1 by 11, which is equal to this current. Delta 2, I2 is delta 2 by delta, which is 10 by 11 ampere, and I3 is equal to 2 by 11 ampere. So with this, we have solved this problem using KCL, sorry, not KCL, KVL method. Now before ending, let me clearly tell you how to write the determinant, how to determine the determinant. 2 3, let us start with 2 3 minus 3, 2 1 minus 4, minus 1 1 0. Now how to calculate the determinant of this matrix? We have some rule. So let us, when you calculate Then you need to suppress the corresponding row and corresponding column in this way. Then you need to conduct cross multiplication, 1 into 0, then minus of 1 into minus 4. So that is why we are writing 2 into 1 into 0 minus 1 into minus 4. Right? Next, let me write the matrix again. 2, 3, minus 3, 2, 1, minus 4, minus 1, 1, 0. So now you need to fixed, or you need to consider these 3. So you need to suppress the respective row, that is the first row and the second column. Right? So then your calculation starts with plus 3. That multiplied with, now the calculation ends previously at minus 4. So in this case it starts with minus 4. So again you need to do minus 4 into minus 1. Then you go this direction, then 0 into minus 2. So we write minus 4 into minus 1 minus 0 into 2. And in the last phase, again we are writing the same matrix. 2, 3, minus 3, 2, 1, minus 4, minus 1, 1, 0. So now you should consider this minus 3 term. So you need to suppress the respective row and respective column, that is the first row and third column. So it will be minus 3 multiplied with, so now the previously it was ended at 2. So now the calculation starts from 2. So 2 into 1, then minus of minus 1 into 1. It's like a cross multiplication. 2 into 1 minus 1 into 1. So this will coming out to be minus 8, sorry, plus 8, because this is plus 4 and plus 4 into 2, 8. And this will be coming out to be 12, this term, because minus 4 into minus 1, 4, 4 into 3, 12. And this will be coming out to be, this is 2, this is minus 1, so 2 plus 1, 3, so it will be minus 9. So it will be coming out to be 11. So in this way, determinant of the matrix is calculated. So with this, I am ending here. So in this lecture, we have discussed KCL, KVL, node analysis, mesh analysis, and we have solved 2 different problems, and we have also understood how to calculate the determinant of any matrix. With this, I am ending here. Thank you.